안녕하세요 여러분, 헬입니다. So in the last video we have talked about all this for SL students and IGCSE. So some basic function definition and all those notations, the two tests, and domain and range for simple functions, and the basic algorithm for composite and inverse functions, and some of the properties for inverse. So today's video is for HO students exclusively. And what we're going to start with today is that we're going to start with some further functions with their domain and range. So what I mean by further functions are something like, let's see, so let's start with some inverse functions, so inverse trigonometric functions. So we have three kinds, right? So first, if the original function is sine x, let's say, then the inverse function of sine would be arc sine, right? And from yesterday, we have sketched the basic trigonometric functions, so sine, cosine, and tangent, right? And we have also looked for their domain and range, right? So, and we also learned how to sketch the inverse function, right? So let's try to sketch the inverse function of sine, right? So sine has a period of 2 pi, so it just repeats over and over again. So let's sketch it like this, right? And note that the inverse will be reflexive over the original function, right? Then that means the arc sine would look like the graph is a bit weird, but it will look like this. So from 1 to from negative 1 to 1, and then this is where pi, and this is where negative pi is. So this is how arc sine looks like. So what we want to do is that we want to see functions, right? But is this a function? No, it is not. If you recall the definition of function, the graph of a function must pass the vertical line test. But does it? No, because as you can see, for a certain value of x, there exists multiple values of y. So that means this is one-to-many function, right? So this is clearly not a function. Then how can we make this to a function? So we don't have to look for the entire region. So what we can do is that we can restrict the domain or range. So let's recall the inverse property first. So in the original function, the domain is any real number, and the range is from negative 1 to 1, right? So in the inverse, the domain becomes negative 1 to 1, right? Because the original function's range becomes the domain of the inverse, and the domain of the original function becomes the range of the inverse. And this is the problem. Why? This is the source. This is the main reason why this arc sine is not a function. So again, we are going to try to restrict the range so that it becomes a function. And how do we do that? We can choose any region, but what I'm going to do is that I'm going to restrict from pi over 2 to negative pi over 2. Okay, so this certain region that we have all the values, right? We have all the values, and then this is clearly a function. So that means if we restrict the range from pi over 2 to negative pi over 2, that means we have an arc sine function, so inverse trigonometric function. So domain becomes negative 1 to 1, and the range becomes negative pi over 2 to pi over 2. All right, then let's look for the second case where we have to see for cosine. So the inverse function of cosine will be arc cosine, right? So let's quickly sketch cosine. So cosine is just a transformed function of sine. So that's how it looks like. Then, and again, the domain of cosine is a real number, and range of cosine is -1 to 1, which is identical to the sine. Then for arc cosine, so again, using the way of sketching inverse, it will look like, so okay, I'll do it one by one. So this is pi, this is negative pi, this is pi over 2, this is negative pi over 2. So this is -1 to 1. So how we can sketch is that we can just simply sketch it like this. So this is the graph of arc cosine. And again, this is not a function. So using this, the domain of arc cosine will be -1 to 1, and the range of cosine is a real number, and this is the main reason why it's not a function, right? So how do we make this into a function? So I'll restrict the range from 0 to pi, and we see that this just repeats over and over again, right? Like that, and then reflexive, that, reflexive, all the way, right? So this is from pi to 0. So we can say that if the domain is -1 to 1 and the range is from 0 to pi, then we can have a function for arc cosine. Okay? Then what about arc tangent? So last one we have is for tangent. So we all know how to sketch tangent. Hopefully, you all know. If you don't, then if you're in HL and if you don't know how to sketch tangent, it's a bit problematic. So this is pi and this is 3 pi over 2. So again, how we can sketch the inverse is that this entire thing is reflexive over y equals to x, right? But it's a bit hard to sketch it just using y equals to x. So what we can do is that just rotate this and then sketch tangent. So pi over 2, negative pi over 2. So this is the asymptote, right? This toward the asymptote, and it will look like this. And then so if we have pi here, and this is what it will look like. So we see that it's just this set is just repeating. Okay, so again, this is 1 to many, right? So it must pass through the origin. So 1 to many, so it's not a function. Then how can we restrict the range so that the function exists? So for this, we know that the domain, okay, so remember the domain for tangent is a bit difficult. So it can be anything except for the odd multiples of pi over 2. And this is how we can write the domain for tangent. So, and for range, it can be anything. So for inverse, we can clearly see that the domain can be anything, and the range can be anything except for the odd multiples of half pi. Then how do we restrict the range so that the function exists? So we can just restrict the plus and minus. So restrict the range from negative pi over 2 to pi over 2. And the domain is everything. And sorry, it's not inclusive. It's not inclusive. So we clearly, these two are the horizontal asymptotes. So y is between negative pi over 2 and pi over 2, but not inclusive. Okay, and this is how we can write it. Or you can just write it like this without using set notation. But again, it's good to know how to use set notation to define range and domain. Okay, so these are the three additional functions that you have to know for HO students. And now, well, there are a bit more things. So the reciprocal of trigonometric functions. So secant, which is the reciprocal of cosine, and cosecant, which is the reciprocal of sine. And you also have to know those things, but I'll talk about them in transformation when we learn how to sketch a reciprocal function, okay? So that's the later thing. So that's it for the further domain and range. And what we're going to do is that we're going to expand a bit for composite function. So it's exactly the same as, the concept is exactly the same as the SL syllabus. So note that since composite function is also a function, it has its own input and output, and just the fact that input becomes another function or any functions. So we have seen whether a composite function exists or not, right? Using the domain and range of those two functions. And we also have seen how to find the original function when you know the composite function. But for this example, so if you were in SL, then if you're in SL, then you just need to check whether the function exists or not. But if you're in HO, you may have to restrict the domain so that you make the composite function exist. So we're going to do that mainly for composite functions. So composite function with domain restriction. And again, this is gonna be very important to find very difficult this is going to be very important to find the range and domain of very difficult functions. So for example, something like this. So you have to find the domain of this, and this is the question from one of the past papers. So I'm going to explain how we can do this too later. But before that, how do we restrict the domain so that the composite function exists? So remember, recall the basic algorithm for composite functions. So if we're looking for f of g, which means that the g becomes the input of f, right? So that means gx would have its own output and input, right? And we already know the mathematical term for input and output, so the domain and range. And fx will have its input and output as well, right? So you can see that how the composite function works is that you first prepare an input and you put that input into gx, right? And that will yield the output of g. And after that, you put that thing back into the input, and then you put that input back. You put that input to fx to make the output. So that's how the composite function works, right? Then let's use the example that I used last time. So and then I asked you to see whether f of g or g of f exists or not. And for the first case, f of g, we have seen that it exists, right? Because the output of g, the inner function, can fit into the domain, the input of the outer function f, right? That's why this exists. But unfortunately for g of f, it does not exist because we see that the range, the output of the inner function is too big to fit in, right? This does not fit in. So for a certain value, the function is not defined, so this g of f does not exist. DNE stands for does not exist. Then let's try to restrict the domain of this so that g of f exists. So quickly copy down, I'll just quickly copy down the basic algorithm for this composite function. So we are looking for g of f, okay? So this is what we have. Right, so our main problem was that this set of the inner function is too big to fit in. Then we can try to make this smaller so that it fits in. And what I mean by fit in is that why don't we just make this set into this so that we are looking for the largest possible values. So what that means is that for the range of f where it was a real number, why don't we change that into equal or greater than 0? So what I mean is that f just change the output of fx like this. Then so fx range has been restricted to 0 or greater. Then what happens to the domain? The domain has to be modified as well, right? Because the range has been changed. So fx is x plus 1. So y equals to x plus 1, right? And that is greater or equal to 0. So that means the domain is greater or equal to -1. So what does that mean? If the domain of g of f is restricted to this, then g of f would exist. So that's the idea of domain restriction, okay? And also, the one thing to emphasize about this algorithm, so many students they don't really use this to solve to understand the composite function. They just directly find the equation. So for example, for this one, you don't really have to do this whole step, because honestly, if you have to find whether g of f exists, then g of fx, which means g x plus 1, right? Which is root x plus 1. So that means if x is greater or equal to -1, then we have the domain, the restricted domain, like this, right? So as you can see, this is much simpler than this method. But the reason why I emphasize on this basic algorithm for composite function is because sometimes you will not be given with the function, the equation of the function. So just gx, nothing else. Then in that case, you cannot find their composition and you cannot find the domain like this. So for those cases, you have to use this algorithm. And an example is in one of the past paper. So I don't know whether you guys could see this image. So it's a past paper question from May 10. So this is the question, okay? You can screenshot the question and then follow with me, okay? So for this question we have, so it's saying that f of g equals to 3 and find all possible values of x, and you can see that the equations are not given. Then how are we supposed to find? So again, use the basic algorithm. So for this case, the inner function is gx, right? So let me just quickly use the other paper. So what that means is that gx is the inner function, and the output for f equals to 3, right? So that means there must be an input for gx, and there must be output as well. And this output goes to the input for fx, right? And then it has the output. And in this case, the output equals to 3. Then let's track back. So first find the input of f. So when fx equals to 3, that means when x equals to 0, when the input equals to 0 and 3, that means this input becomes 0 or 3. Then what does that mean? Output of gx is 0 or 3, right? That because output of gx has been just sent to the input of f, right? So the output of g must be 0 and 3. Then we can track back the input, right? Because when g equals to 0, that means the input is -1 to 4, right? And when g equals to 3, that means the input is 1 and 2. So that means the answer is -1, 1, 2, 4 for this question. Okay, so this is the reason why I emphasize this definition, this basic algorithm for composite function, because again, for most of the calculation, as long as the functions are defined, then this just directly solving would be much better, because we have to consider the amount of time we use as well, right? But for the case like that, just right now, the example like that, we have to if you understand this well, then no worry, okay? So please understand the basic algorithm as well, okay? So that's a very easy example for domain restriction, but so okay, for domain restriction, I'll give you some more questions for the sample test, but let's try this first. So this it's not that difficult, but as long as it's a bit more difficult than any other questions that you've seen so far. So we want to find the domain of this. So you can see that this is a composite function, right? Why? Because we can let gx be arcsine, and we can let hx be ln x, and this is just composition of g and h, right? G of f, and that's fx. So you can either use composite function, so all this algorithm again to solve this, but you can also use what we already know for domain and range of these two functions. So remember, for inverse trigonometric function, in order for arcsine to be a function, the range has to be this and the domain has to be that, right? So domain should be from -1 to 1, right? That means ln x, right? This input must be from -1 to 1. Then that means x should be e or 1 over e, right? Very simple. But how can we use the composite function to do this? Well, it's simple as well. So hx becomes the input function, right? What's the domain for ln x? The domain for ln x is x greater than 0, right? And what about the range? Range can be anything. And for gx, what's the domain for arcsine? It's -1 to 1. And the range You can use any set, but I'm gonna use from pi over 2 to negative pi over 2. Okay, one thing, does this exist? And the answer is no, right? Because clearly this is too big to fit into this, right? This one, it means set of all real number. And we have to fit this set of all real numbers into this set of negative 1 to 1. And clearly we cannot fit this in, right? So first, the composite function, this does not exist. Then what does it mean by find the domain? We just need to find the domain so that it exists. Okay? And how do we make this exist? So again, as what we did for domain restriction, we copy this here. Because if we restrict the range of the input inner function, then we can fit that restricted range into the input of G and then make the function exist, right? So let's restrict the range to this set. So for H range, we make it to negative 1 to 1. That means the domain has to be restricted too, right? And how do we do that? Again, what's y here? Y, it's hx, the output, right? Which is ln x. So ln x is between 1 and negative 1. So that means x is from 1 over e to e. So as you can see, just directly calculating is much faster, right? And much simpler. But what I want to emphasize is that all this stuff, this thing, is actually from here. Okay? So please understand this first and then go for the computation. So in your exam, exam or test, so since you have to consider the amount of time you spend on for each question, so I would recommend you to do this. But before you directly use this, you should have enough practices before your exam or test with this method, this definition. Okay? So that's it for the domain restriction for composite function. And now we're going to move to the domain restriction for the inverse. So we have seen some cases where the inverse function is not defined, right? I mean, inverse function, does not exist. So remember that in order to have an inverse function, the original function must be on one-to-one corresponding function, right? Then does that mean we cannot find the inverse function for for example, many-to-one functions? So for example, quadratics or some particular cubic functions? Well, the answer is you can find it by doing the domain restriction. And how do we do it? So let's start with a very simple case first. So we already know that unless a function is one-to-one correspondence, the inverse function does not exist. So since x equals to y squared, as the sketch indicates, it's many-to-one, right? So a certain value of y, there are two values of x. So it's 2-to-1 or many-to-one function. So clearly this should not have inverse. And it makes sense because if you sketch the inverse, it will look like that. And for a certain value of x, it has two values of y. So it's one-to-many. So it's not a function. Then how can we restrict the domain of x squared so that the inverse exists? In other words, you just need to make this quadratic function into one-to-one. But it's not one-to-one. How do we make that into one-to-one? Very simple. For this. Why? Because you just need to look at this. Right? Or you just need to look at that. As what we did for the inverse function of trigonometry in the very beginning. What we did here is basically example of domain restriction. So we restricted the domain, right? So basically what we did is that for sine x, we restricted the domain from negative pi over 2 to pi over 2 so that the inverse exists. And it's the same for cosine and arc cosine and arc tangent. And it's exactly what we are trying to do. So what we can do is that we can just either look at this, right, or look at this. Because if we just look at one of the half, it becomes 1 to 1. So you can choose anything. So let's say we just want to look at x greater or equal to 0. Then this is what the original function looks like. Then the inverse would be this, right? And this is y equals root x plus. And if you want to look at this, then it's also fine. So we're looking at this region, right? So that means the inverse would be this, y equals negative root x. Okay, then can we get this from the sketch only? The answer is no. You can also find this you can do this domain restriction by finding the inverse equation first. But honestly, this is much better. This is easier. This is easier than finding the inverse equation. So, for example, well, the inverse of that. So first. So we all know how to find the equation of the inverse. So first, replace all x and y, right? So x equals to y squared. And then second, you rewrite the equation into y in terms of x. So y equals to plus minus root x. So we have two different values for y for a certain value of x. That's why it wasn't a function. So instead of looking at both of them, we can just look at them separately so that the inverse exists. Okay, that's it. That's basically what we are trying to do for domain restriction. And so we have seen a very easy case here, right? So I'll not talk about the harder case here in this video. I'll post some questions. I'll include some hard questions with this in the sample test, and then I'll also tell you how to solve them so you can download that sample test to do it. Okay, and again, I didn't add any advertisement, or you don't have to register for or anything. You just need to go to my blog and then download it, and it's free. It's completely free. So that's it for the domain, domain restriction for the inverse. So we're almost done because, well, the last video was 2 hours long, so we actually talked about like almost everything. But some more varieties of types of functions that you have to know other than like composite or inverse. So as mentioned briefly in the last video, for HO student, you have to know first. You have to know the self-inverse functions. So what it means by self-inverse function is that the original function is the inverse and inverse is the original function. What does that mean? So any function that satisfies this. So an example is an identity function, which is y equals to x, right? So y equals to x, the inverse is also y equals to x, right? And something else, y equals 1 over x. Because the inverse is also y equals 1 over x, right? And the main point, the main point for self-inverse is, this is where the thing is very important. So remember that in inverse functions, in order to find the intersection between the original function and the inverse, we could equate the original equation with y equals to x, or equate the inverse equation with y equals to x, right? Because the intersection intersects with y equals to x, the identity function as well, right? But for some functions like self-inverse function, for example, some intersection points may not intersect with y equals to x. So for example, this self-inverse, it also has intersection with its inverse at, for example, something like x equals to 2 and y equals to half, right? But clearly, that does not intersect with y equals to x. So be careful that this only works for non-self-inverse function, okay? Or the function where it does not have a region with self-inverse. So yeah, that's one time. And second, this is probably the assumed knowledge, I think. So even function. What's an even function? Even function is a function where this holds. So the negative input and the positive input is the same. So an example is something like y equals to x squared. So we see that, for example, if x equals to -1, y is still 1. And if x equals to 1, y is still 1. So this holds, right? And for the characteristic of inverse function is that it is always reflexive over y-axis. Because all the positive value here is the same as the values here, right? So it's reflexive over y-axis. And one last thing is that you have to learn odd function as well. So odd function is where this holds. So what it means is that, for example, x cubed. So when you put -1, right? So f -1 is -1, right? If fx is defined as cubic function. And f1 is 1. So we see that f minus 1 is minus times f1, and minus 1 times f1. So this is what it means by an odd function. And the characteristic of odd function is that it is reflexive over the origin. And what it means by reflexive over the origin is that you rotate it 90 and 180. Okay? So not like this, but rotate to clockwise or clockwise or anti-clockwise by 180. So it looks like that, right? And then it looks like that. So that's the characteristic of odd function. So that's it for the basic function for SL and HL. And in the next video, I'm going to talk about transformation. So for HL students, you will learn something a lot more than SL. So something like reciprocal or some hard rational with some weird, not weird, but different asymptotes. So see you in next video. Bye.